Hello everyone, my name is Nestor Tiglao and I'm here to present our paper entitled Hardware Accelerated Blockchain-Based Authentication for the Internet of Things. For my presentation, I'll follow this outline. First, I'll provide the motivation of this work. Then I'll present some of the related work. Then I will go over our methodology and then present our results and analysis, and then finally end with a conclusion and future work. The motivation of this work is really the desire or the need to provide more secure Internet of Things transmission. And nowadays, there is a gaining popularity for smart devices and IoT devices, namely smart plugs. And smart plugs are deployed in homes, and also in commercial settings where you put a plug into an electric socket and that plug will automatically measure energy consumption. However, we've seen that most of these devices use traditional authentication, and a lot of them do not even implement efficient security and authentication. So the issues of concern here are, number one, privacy and security. With projections for IoT where the number of devices could exceed billions in the coming years, there is a need to ensure that security mechanisms are put in place for these IoT devices. And then secondly, since we're looking at a very large number of devices, then we should also look at scalability. And then, of course, with scalability and security in place, it should not be at the expense of the performance and reliability of these devices. Since these devices are designed to perform day in, day out, year after year, and therefore we should put in place security mechanisms that allow it to perform and become reliable with the passage of time. Now, that's why there has been a lot of previous work in the area of lightweight cryptography, specifically ISO IEC 29192 is a document that defines techniques in lightweight cryptography, ideal for low-powered and simpler devices such as RFID tags, sensors, contactless smart cards, healthcare devices, and so on. Now, this document classifies or categorizes solutions of lightweight cryptography based on their implementation. So in terms of hardware implementations, the chip size and or energy consumption plays a big role in implementing this lightweight cryptography. For software implementations, the code size and or RAM plays a huge part in this case. So the question is, why should we look at lightweight cryptography for IoT? Well, there are two main reasons. Number one is that we want to maintain efficiency of the end-to-end communication. So take note that most of these IoT devices are lightweight, resource constrained, and they're designed to operate on low power, okay, and they should be as much as possible low cost. Secondly, we want to implement very high-end, very secure and scalable cryptographic mechanisms that will run on these lower resource devices. So that's why this has been the motivation for us looking at this work. So, and one technology breakthrough that has been key in being able to solve this problem is the concept of blockchain, which started from the work on Bitcoin, which is a decentralized currency system. However, what underlies this Bitcoin mechanism is a decentralized ledger where you have all these transactions are stored in this distributed ledger called the blockchain. So here's an example of in Bitcoin where it uses private key, a public key, and a Bitcoin address, which refers to a particular Bitcoin currency. And as you can see, it uses one-way functions, one-way cryptographic mechanisms. So it can, for example, from the private key to the public key, there's a one-way hash or one-way function using elliptic curve multiplication. And then from the private key to a Bitcoin address, there's a hashing function. And what the hashing, or what this one-way function does is that it's very, very quick and very is very conducive for implementation in hardware. And the blockchain mechanism uses what you call a Merkle tree or a hash tree, where, as you can see in this example, if you have a message, it can be broken down into different blocks, and each block here will be operated on and generate a hash. Okay, and the hashes of those individual blocks are then combined until you arrive with the top hash. Okay, and this one becomes a way to authenticate the whole message. Okay, and this becomes very efficient, especially when you're dealing with a very large data block. So this is a very good mechanism. So in our methodology, we will implement AES 128 and the blockchain hashing algorithm, which is the SHA-256, and we'll implement that on a peripheral device called the NXP Kinetis board. And this is a peripheral device, so we can use it in conjunction with our existing device for the smart plug. And the acceleration function of this hardware, this small board, is called the memory mapped cryptographic accelerator unit. For the transceivers, we will use the low-cost NRF24L01 plus transceivers. And since we are considering that there could be multiple smart plugs in one area, we will use TDMA for multiple access. To analyze the performance of our system, we will use 10 vectors from RFC 4231, and we will look at the processing times, and we will compare the software-based implementation, which runs on our Arduino board, and then compare it with a hardware-accelerated version where we now use the Kinetis board to perform the cryptographic computations. So here's a diagram showing our network where we have our smart plugs here, and there's a shared key that is stored in the smart plugs, and these smart plugs then send data over through a gateway all the way to the server. So in the physical sense, we use a Raspberry Pi as our gateway controller, and our smart plug uses is an Arduino 101, and we connect the NRF24L01 plus transceivers using SPI to these boards, and we also connect the NXP Kinetis peripheral device using I2C to our smart plug. And here, once the peripheral device computes the encrypted data using AES 128, then it can now send it all the way to the server through the gateway. So for each message, as is the case of it's being used in Bitcoin or blockchain, we use hash-based message authentication codes, or HMAC. Now the HMAC uses or combines public keys, private keys, and a hash for the message authentication. Okay, and here's the formula for how we derive the HMAC ciphertext. Now there's a well-known practice with message authentication codes which truncates the outputs, because in general the encrypted data could be very long. Okay, since we are working with resource-constrained devices, we can truncate that data and then process the truncated data. Okay, so in the case of, for example, for HMAC SHA SHA-1-80, the computed SHA function is truncated to 8 bits. Okay, so and then what we will do is implement encrypt, then authenticate mechanism. So we encrypt it first, and then we generate using a hash function a key, and then what we do with that is that we generate the ciphertext plus the message authentication code appended to it. Okay. So the way that our system operates is that like in the blockchain, we first authenticate the Genesis block, or the first block of the blockchain. Okay, right. So this is shown here in algorithm 1. This is the AES-128, and then this is the message HMAC. Okay. All right. For subsequent blocks, we authenticate also using algorithm 2. Okay, if, for example, in our case, we tested 4 devices, each one sending data to the gateway, then each one will compute the data that they will send, and then the server will check the hash of the previous data. So depending on, so in this case, since this TDMA, each one will take their turn in transmitting to the data, transmitting to the gateway. So here's just a picture of the hardware that we used. So here is the Kinetis Freedom Board, connected now to the Arduino 101, which is our smart plug. And this is our transceivers here, and the Raspberry Pi here acts as our gateway. So for the software component, we develop a database that shows that stores the data sent from the smart plug, as well as their hashes. So when we transmit them, they have their own hashes, and we transmit that over to our server and authenticate that. So in terms of the final results, we implement both the AES encryption for authentication and the SHA-256 for our HMAC, for our hash-based message authentication. And we compare the performance in both Kinetis and Arduino 101. And we see here the speed up factor derived from using hardware acceleration. So 7.94 for SHA-256 and 5.53 for AES-128. Okay. To conclude this presentation, we highlight that device and data integrity are important to secure IoT devices, and we see that lightweight cryptography is a viable solution to implement device and data integrity for resource-constrained devices. And we also saw that hardware acceleration provides significant speed up compared to purely software implementation of cryptographic algorithms. Thank you very much for your kind attention.